There we go. So we left off, the lights here. We left off talking about some trig problems, right? These trying to simplify these trig limits, and they're a little trickier maybe than the others because they require you use so many trig identities, right? So here's the main one that we use, right? The limit of sine x over x as x goes to 0 is 1. We got this other one that, like I say, I mean, you don't use it very often. It's there if you need it, but you rarely use it. We looked at that guy. We looked at that guy. We looked at something like that. Those are real common. And then we ended up, is this the one we left off on? I think it is. Isn't this the one? Lucy, is this the one where you found a mistake? No, it was that one. That one right there. Yeah. Okay, we were doing some stuff on this one, right? This is a pretty advanced one, but I wanted you guys to see one really advanced example. The problem with this one, remember, is that the angle is not going to 0, right? And so that makes this a little harder to deal with because our special trig limits that that we can use to eliminate the indeterminacy, they're all geared towards the angle going to 0. And so what we're able to do here, this is kind of a different technique where this is a pretty high level thing for a first year calc class, but you guys can handle it. We want to make a variable substitution so we can write a different limit where the variable is going to 0. And we said that if theta is going to pi halves, then we could define some new variable x in terms of theta that goes to 0. As theta goes to pi halves, if we define x as theta minus pi halves, then x would go to 0, right? And so we could make that substitution. Well, we need to be plugging in order to convert this limit from thetas to x's, we would have to plug in for theta, right? So we need to take this substitution and rewrite it in a way where we isolate or solve for theta. So theta ends up equaling x plus 1/2. If we plug all that stuff in, then we get this really ugly looking limit. And in the bottom one, we had a 2x, so we got to distribute the 2. What we end up getting in here that looks really kind of bad is we've got these sines and cosines of sums, right? And so we needed to go back to our trig identity sheet and remind ourselves, well, how does that work? If I have sine of a sum of angles or cosine of a sum of angles, what does that look like? And I did a little, I kind of thought of a way I could build some flashcards for you guys. I'll give you sheets and I'll build you some flashcards in preparation for we'll just do a little quiz over this at some point. I'll tell you dates on it. I'll give you like a week to memorize this stuff, so you'll have plenty of time. If we use these trig identities, sine of a plus b and cosine of a plus b with our angles up here, well, what do we end up getting? So we get, on the top, we get 2 minus 2 times sine of x times cosine of pi halves, which is 0, plus cosine of x times sine of pi halves, which is 1. Okay, on the bottom, we end up getting cosine of 2x times cosine of pi, which is -1, minus sine of 2x times sine of pi, which is 0. So in both cases, something good happens. We get one of the two terms is going to 0, okay? And we're left with this. We're left with 2 minus 2 cosine x divided by 2, and this is where there was a mistake that Lucy caught. And I was wondering, I kind of, after you guys left, I was going to take a look at this and try to just finish this one up, because I haven't done this in advance, but sometimes I like to not do these in advance, so I have to kind of think a little bit too. And she had caught there was a sign error there, which was kind of messing us up. So in your notes, that might have said plus, that should be minus, okay? So on the bottom, we end up with 2 plus 2 times cosine 2x times -1, so there's the minus. And now we get to a point where, okay, we can cancel the 2's. So this is looking better. We get 1 minus cosine x over 1 minus cosine 2x as x approaches 0. Okay, how are we doing so far? Give me a 1 to 5 on this one. And I'll publish this in the notes. I mean, this is a pretty big one, right? There's a lot to follow here. So assuming that, you can get to a point where if you go back and review things, which you might have to, we can get to here okay. Now the question is, where do we go from there? If I try to plug in 0, I'm still getting 0 over 0. I haven't canceled anything important yet, right? What do you think? And this is, I'm going to draw your attention to something. When you see this, what's that? There's a flag that's going off, hopefully. As you start to develop more intuition with math and with calculus and with trig, when you see something like that, what's maybe starting to pop into your head? What's a reasonable step then? The conjugate, right? But see that because 1 minus cosine x times 1 plus cosine x would give us 1 squared minus cosine squared. Well, 1 minus cosine squared is what? From our Pythagorean identities, didn't I drop a bunch of Pythagorean identities on one of these? Thought I did. I don't know where it is. Maybe I didn't. Thought I did. Sine squared it is. Yeah, I thought I had done that on a different page, but if I did, I can't find it. You're right. It's sine squared. I think that was a different day, maybe. Huh? I don't know. Possibly. Right. So that's sine squared. So that's a great thing for us to do. We can multiply this top and bottom by 1 plus cosine x. Right. And that's going to give me then, on the top, when I multiply these conjugates, I get 1 minus cosine squared x, which is equal to sine squared x. Okay, that's good. Why is that so good? Well, for one thing, because we've got sines. If we go back to this page, we've got signs here that we know what happens if I divide the limit of sine x by x, right? So just having a single sine term in the top looks very promising. Oops. There we are. Okay, what about the bottom? So on the bottom now, I've got 1 minus cosine 2x, that quantity, times 1 plus cosine x. The 1 plus cosine x, that looks ugly, but when I evaluate the limit, that does not go to 0, right? Which is good. What could I do with this 1 minus cosine 2x? Well, that brings us to our double angle formulas. Right? We know that sine 2x is 2 sine x cosine x. Cosine 2x, we can write it in its basic form, it's cosine squared x minus sine squared x, but we could choose any of these. We could choose to substitute for cosine squared or sine squared, depending on what we want to be left with. Well, what do you think we want to be left with here? On the bottom. Do I want to have sines or cosines in there? Probably sines, right? I've got this sine squared on the top. I probably want to try the one with sine squareds on the bottom. Okay, and look what happens when I make that substitution. So we're going to go from here down to 1 minus cosine 2x is the quantity. We're going to use this guy right here. 1 minus 2 sine squared x, right? And then I've also got, I'm going to have to make a little more space, aren't I? I've also got on the bottom this 1 plus cosine x. But look what happens here. When I distribute the negative, the 1's are going to cancel, and I get a 2 sine squared x, right? Which is good because I erased it, but we've got this sine squared x on the top that's going to cancel with that sine squared x on the bottom then, right? Everything in the orange, this orange sum is going to become a 2 sine squared x. And then I've still got this 1 plus cosine x down there. But that's big time cancellation right now. If I cancel that sine squared and that sine squared, that's what was causing the indeterminacy, right? Those are the ones that were going to 0 here, okay? And we're just left with then, on the top, 1. On the bottom, we're left with 2 times the quantity 1 plus cosine x. As x goes to 0, cosine of 0 is 1. So I end up with 1 over 2 times 2 equals 1/4. Okay? And I get that's a pretty hard problem. But as you know, I think you have to go through some of those. Even if you don't completely follow every step, you kind of, there's parts of that are going to stick. And I think the important stuff is kind of what happens down here. Now, I don't want to give you the impression that you have to get these right on the first try. I don't. I mean, when you're going through these things, you can't always think that many moves ahead and know exactly which of these identities you're going to use. So frequently, you try one and it doesn't work. And so then I go back up to the step before I plug that one in and I cross everything out and I try the other one. Okay, this is one reason why it gets really important as you get into college to write your work down accurately, you know, because there are so many false steps. I mean, I don't want to scare you, but I can remember some times in college where, man, I mean, especially in physics, I had a quantum mechanics problem set one time, and it was 4 problems, and the thing took me, I mean, it was like 80 pages of work, you know, and so many wrong, it was a brutal one. I mean, that's like a legendary one, but it was terrible. And there were so many wrong turns in there. But if at that point, I had already learned the value of being, moving vertically through your work. Don't be going horizontally, always go vertically. So step leads to step leads to step. So when you find something wrong, you can trace back up to where you try, you know what I mean? You can trace back to where things went wrong and start over from there, start a new branch. Okay. Anyway, enough of that. Questions, comments? Okay. All right, last issue for this next problem set, the practice 3. It's called the Squeeze Theorem. This is a really cool theorem. What this is telling us, and you guys in the back, this is another one, if you want to, I'm taping this, but if you want to watch this, this is something that shows up a lot on your stuff too. So the Squeeze Theorem, what this says, it says that if you have 3 functions, f, g, and h, and they have the following properties. They have the property that for all x in some open interval containing c, except possibly at c, one or more of those functions may not even exist at c. But for all the values surrounding c, these 2 conditions are true. If g of x is greater than or equal to f of x and less than or equal to h of x, for all values in this open interval, except possibly at c, and if the limit of the bottom function, right, because I've got these 3 functions that essentially, if I graphed them, they'd look like this, wouldn't they? G of x is the middle function on this interval, f of x is the lower function, and h of x is the top function. So it looks like this. Everybody get that? They're bracketing f of x and h of x are bracketing g of x. Sometimes you can call this like a floor function, and that's a ceiling function. And this is trapped in between. Okay, well, what happens if the limit of the bottom function as x approaches c is equal to the limit of the top function as x approaches c? Let's just say it has some value L. Well, what's that doing to the middle function then? if the middle function is defined as being between f of x and h of x, between the bottom and the top functions, for all values on this interval surrounding c, then what must be true? If ants were walking towards c from the left and the right, what value would the middle function have to be approaching then? Well, it'd have to be approaching whatever value the squeezing functions were approaching, right? Because they're both approaching the same value, and so they squeeze the middle function to that same limit. Everybody see that? Okay. Does the middle function actually have to have that value? No, it doesn't matter, because limits don't care what actually happens at c. They only care what happens as you approach c, right? It might be, it's entirely possible, that there is a hole in the function. Maybe there's a hole in the function here, in that middle function, and the value's up here or something, right? Doesn't matter, right? Limit doesn't care. Limit just wants to know what value does the ant think he's approaching, and if we know that for all values except c, the middle function is between the bottom and top functions, and the bracket, the top limit of the top and bottom functions converges on the same value, then the middle function has to be squeezed to that same limit. You give me 1 to 5 on that concept. Okay? Okay, good. All right, so then how do we use this? Well, we use this in a number of ways. Here's an example. Okay, these are the kinds of questions you run into, like on an AP test, for example. So it says something like this: suppose that g of x is greater than or equal to negative the quantity x minus 2 squared minus 3, and less than positive the quantity x minus 2 squared minus 3 for all x in an open interval containing 2. Okay? Find the limit of g of x as x approaches 2. We don't even know what g of x is, but how could I use the squeeze theorem here? Let's go back to that page for just a second. So here's the squeeze theorem, right? If these two conditions are met, then this is the outcome. But this is a big if, right? You have to be able to check both those boxes. If you meet the criteria, then we can guarantee the outcome. This is another one of those existence theorems, right? You meet the criteria, then something exists. And in this case, we know what it is. Okay, so do we meet those criteria? Do we meet the first criterion? Is g of x between the bottom function and the top function? It says it is, right? It says it is right there. So criterion 1 is met based on that statement right there. Everybody get that? Okay, what's the second criterion that we have to meet? In order for us to know the limit of g of x, what else has to be true? Let's go back. Okay, yeah, so the limits of the bracketing functions, the top and bottom functions, have to approach the same value, right? In order to squeeze the middle function to that same value. It wouldn't do us any good if the limit of, when we took these limits, if the limit of this bottom function as x approached 2 was different than the limit of the top function, well, we wouldn't know what g of x, what its limit was. It could be anything in that range, right? But what happens here if we take the limit of the bottom function? That's this guy right here, right? The limit of that function. So the limit of negative the quantity x minus 2 squared minus 3 as x approaches 2 is what? -3. Yeah, good. Okay, how about the top function? So that's this guy right there. So the limit of the quantity x minus 2 squared minus 3 as x approaches 2 is what? What's that one? -3. So there's criterion 2 has been met, right? So what do we know for sure then? What's the outcome? Yeah, limit of g of x has to be -3 by the Squeeze theorem. By the Squeeze theorem, the limit of g of x as x approaches 2 is -3. That's pretty cool. Okay. So that's mainly how you use these. Okay. The problems on the Math Excel problem set are all kind of like this. I mean, they're pretty straightforward. I do want to show you guys something different. And this is where maybe you guys in the back want to maybe just pause. I mean, it's like I'm recording it, so it's up to you. But this is something I didn't do last year that I thought maybe I'd add. So how could we actually use the Squeeze theorem? And this is like a proof. How could we use the Squeeze theorem to find a limit like this that's indeterminate, right? I end up with the limit of 0 times sine time. Well, 1 over 0 looks like infinity, right? And that's another kind of an indeterminate form. There are lots of indeterminate forms. The only one that we've really talked about is 0 divided by 0, right? That means more work. It's indeterminate. But we have tons of other kinds too. Like if I take limits and I get infinity over infinity, that's indeterminate also, right? We've got to do some more work. 0 times infinity is indeterminate. Infinity minus infinity is indeterminate. We don't know what that's going to be, right? There's all different kinds of indeterminate forms. And this is another one. So what could we do here? I just want to walk you through just a little proof. And once again, this would fall into that category of, okay, this is pretty high level, but today's a high level day, I guess. I want you guys to see something like this. So for one thing, we see here that if I want to use the Squeeze theorem, I'm going to kind of give you a motivation for why this is going to work the way it is. Well, we want to be able to bracket something between a lower and an upper value, okay? When we look at a problem like this, we recognize we've got sine of something, right? If I have the sine of an angle, sine is always bracketed between what two values? Sine of any angle. What's the biggest the output of a sine function could be? 1. What's the smallest it could be? -1, right? If we graph a sine function, it just wiggles along and it's capped at 1 and -1. And the wave train just oscillates between those two values infinitely, right? Okay, so we might start with just this sine part, right? Because we know that sine of anything is going to be bracketed between -1 and 1. Okay, and that gives us a good place to start because it allows us to create some expression that's trapped between a lower and an upper value. It starts to look a little bit more like the Squeeze theorem. Okay, well, if that's true, if sine of 1 over x is greater than or equal to -1 and less than or equal to 1, another way of saying that is its absolute value is less than or equal to 1, right? And you remember this goes back to algebra 2. Remember our pattern. If we have the absolute value of anything, absolute value of, I'm going to say sine, oops. If the absolute value of some function is less than some value, we could trade that for the compound inequality. Then whatever's in the absolute value is greater than the negative number and less than the positive number. It's an and statement, right? This is one of our patterns we have for solving absolute value inequalities. Okay, so we've got this. If we were to multiply both sides by the absolute value of x, and the reason we're doing that is because in the original problem, we're taking a limit of x times this sine function. Why do we multiply by the absolute value of x? Because that's always positive. And so we know we're not flipping the inequality, then we can guarantee the inequality stays the same direction. Everybody see we'd open a big can of worms here. If I just multiplied by a random x, that would make this much, much more difficult, because then we'd have to consider, well, what if x is positive? What if x is negative? It becomes a lot more complicated. We know the absolute value of x is always positive, right? And we have another property. You finish this for me. The absolute value of a times the absolute value of b is equal to the absolute value of what? A times b, right? Everybody agree? Doesn't matter what the signs of either one of these things are individually, because the absolute value is going to make it positive anyway, just like they're individually made positive here. And positive times positive is positive, okay? So if we do that, we can wrap this absolute value of x with the sign, and then we can say something like, okay, well, what did I end up getting? I had to multiply everything by the absolute value of x. So I multiplied the 1 by the absolute value of x also, right? So we get this statement right up here like this, okay? Well, then we know, again, if I have an absolute value inequality like this, I can rewrite it as a compound inequality, where the function inside the absolute value is in the middle. It's greater than or equal to the negative and less than or equal to the positive outside quantity, okay? All right, so then what's true here? Well, we're taking a limit as x approaches 0. Well, what's the limit of this bottom quantity? What's the limit of negative absolute value of x as x approaches 0? It's 0, right? What's the limit of the top quantity, the absolute value of x as x approaches 0? It's 0. So what do you know? Then there's our proof, right? We've met the criteria for the Squeeze theorem, right? We've met the criteria right here. There's criterion 1 right there. We can check that off. And here's criterion 2. The limits converge. The limits of the outside functions converge on 0. So what's the outcome? By the Squeeze theorem, we know that the limit of the middle function has to go to 0. That's pretty cool, huh? Right? And I've at one point sat out there like you guys and thought to myself, well, yeah, that looks great, but I'd never think of that. But you will. If you do this for a while, I promise you, you will. This stuff, it's just a process, and you gain intuition by doing problems. Calculus, the only way to get good at calculus is to do lots of calculus. But as you do lots of calculus, it's just amazing. By the end of the year, you'll look back and think, oh my God, that stuff was so easy at the beginning of the year. Piece of cake. You know, it really, I mean, you just get better and better and better all the time. Okay. I'm not going to do that one. That's probably overkill. I wrote up another one, but same kind of thing. You guys are good to go. When are we out of here? 3 minutes. Okay. So yeah, that's a good place to stop anyway. So you've got both of those assignments. I think I've got due dates on them. I think they're published. Does anybody know for sure, like the 1.2 practice 3, is that one up there? Tomorrow night. Okay, I think I'll move that off one day because I want you to be able to ask questions. Let me look at this. Okay, so the 1.2 practice 2, that's just the one on like rationalizing techniques and things. You've probably already done with that one. But let me look. I want to check the due dates on the other ones. Just make sure everything's good. $10.5. Yeah, why don't we make it do $10.6 instead? So this change may not show up in Google Classroom, but that's not important. It's in Math Excel. How many people have gotten a start on the 1.2 practice 3? Oh, you finished the whole thing? Oh, shit. Hell, you're supposed to be doing that. At least you're honest. Yes, Amber. On the free response? Yeah, I could do that. Okay. Mm-hmm. So Amber, you guys will be up front tomorrow. So instead of them being due, they're due tonight, right? Technically. Okay, so I'll change them so they're due day after tomorrow, so you can get questions answered tomorrow if you have any. Yeah. Oh yeah, exactly. Yeah, no, that's a good point. Yep, that makes sense. Thank you. All right, have a good one. How's this stuff coming, ladies? Is it good?
Yeah.
Good? Are you good on this? Okay. Julie, you're on top of this. It's a lot easier this year, isn't it? Yeah, no, you're right on top of this stuff. No, good for you.